and 2011. And since 2011, she is Max Planck Institute Director in Dresden. Her research interests are design, synthesis, and physical characterization of new quantum materials. She has done pioneering work on Heusler compounds, topological materials. Recently, her focus is chiral materials, and she has received numerous awards and honors. And let me tell you some of them for her really outstanding work. So she has received in 2019 the McGrody Prize for New Materials from the American Physical Society. She has received in 2022 the Max Born Prize and Medal of the German Physical Society and Institute of Physics. She has received the Wilhelm Oswald Medal of the Saxon Academy of Sciences. She has received in 2001, I think this is an interesting one, a nice one, the Order of Merit of the state of Rhineland-Pfalz for the foundation of the first lab for school students at the University of Mainz with a focus on female school students. She's a member of the National Academy of Science of the US and many other National Academy of Sciences. And I think I should stop here, Claudia, otherwise we are not going to start your talk. So today, Claudia is going to tell us a little bit about her research. And the title of her talk is indeed Topology and Chirality. So please, Claudia, the floor is yours. Or the screen is yours. You are muted. You are muted, Claudia. You have to unmute yourself.
Rosa, thank you very much for the very kind introduction and the nice words, since we know each other since a very long time. And I also happy to see Nandini, with whom I have also very nice collaborations. And I'm looking forward to have even beyond my abilities at the moment. So to see Laura and others really good women in science here. And I'm also happy to see nice colleagues from Germany like Johanna Stachel, who spoke also about chirality. I didn't fully understand, but I hope one day I have the chance to talk to you in person, because we are interested in some sense in chirality and the chiral anomaly. And yeah, and I'm super happy to be here at this WOW Physics meeting and learn about fantastic young people, young women also. And I'm sure we have a very good time in science since the number is increasing. Okay, so I want to talk about topology, and I have to say also, so I can also make a connection to the talk of Christina Koch, so who liked also chirality. And you learn already that chirality is everywhere. Okay, and there are a lot of open questions. Therefore, I couldn't ask the question I wanted to ask Johanna, but maybe later in time I have the chance. So do we really understand the fundamental broken symmetry of chirality? And there seems to be some good ways. So what I learned from high energy physics and even from optics and theory, that we can maybe make homochiral materials, molecules, with the help of chiral light, so which I think is very nice. So my idea is that something, the concept of topology and the concept of chirality can maybe bring us also forward to develop new ideas in the sense of chiral symmetry breaking. And now I hope I can, okay. Continue. Okay, so as I said, so more or less you learned already about many things today about the chirality of molecules. This was Christina's talk, and the chirality of fundamental forces is like the beta decay here as an example of cobalt, where you also have fundamental broken symmetry. And the very recent field, which more or less can bridge many different fields, is the field of topology, which is something which we know from mathematics, and many other areas also talking about topology. But in condensed matter physics, it's quite new, and it allows us to use particles in condensed matter physics maybe to understand a little bit more what is possible in other fields of physics eventually. So therefore, I think it's really very exciting. And the field of topology simply started with the discovery of the quantum Hall effect of Klaus von Klitzing. And at this time, everybody thought it's a quite exotic effect. So you have a very complex system, like a two-dimensional electron gas. So you must make multi-layers, and they have to have a certain degree of cleanness. So the electron must be quite mobile and so on. Even Klaus, I think, thought that the samples were really essential for this. And then he simply measured the Hall effect, the resistance in a magnetic field. And what he found out is that you can have this contrast value. And this is really very nice plateaus, very fundamental, but you need to measure this. You need very low temperatures and high fields. And if you apply these high fields to this free electron gas, which you know in condensed matter physics is if you have no, so then you can localize the electrons in the sample, in the inside the samples, and at the edges you observe something very special and unusual. So you observe these edge states here, which are here drawn in red and blue lines. And these are topological protected. So if I, for example, make here another wedge into the sample, so I think this topological edge states go simply around. And these are electrons where the spin and the momentum are locked. And in the moment when an electron is there, where the spin and the momentum locked, the electrons are chiral. And so they cannot be scattered into each other. So this was discovered in 1984, and he got the Nobel Prize very fastly. And so for a long time, nothing has happened. So, but nowadays we even found, or at this time also people found sometimes in crystals, you can even find these new plateaus, and even the fractional quantum Hall effect, you simply take these crystals, and recently people really observe it very carefully, and they talk about the 3D quantum Hall effect, so which means we simply take a simple single crystal, put it on some sample holder, put it in our machine, we press a button. We have still to go to low temperature for these crystals, but for graphene, monolayer of graphite, it's even possible to have it at higher temperature. And you see in a measurement, again, simply resistivity measurement in a magnetic field, that you can have this kind of plateaus and even fractional values. And so we can then interpret this single crystal, since it's also quasi two-dimensional material, as layers of this two-dimensional electron gas. And we can even see the interaction between the layers as a parameter which can be seen in the measurement. So, but the field of topology was more or less still not really very active at this time. And but already in '88, you see here, Haldane, he had the idea, what for me as a condensed matter person who likes to make materials, is quite obvious. So that if you simply take a material which is non-magnetic and you need a large magnetic field to see an effect, you can simply take the magnetic material, okay, find the right magnetic material, then you don't need the magnetic field because you have an intrinsic magnetic field due to the magnetic moments of the magnetic ions. And he proposed this as a quantum anomalous Hall effect. It seems to be not so many people paid attention to this paper, I have to say. It's a theory paper because nobody did search for this magnetic material. And then recently in 2005, so people also know if we deal with spins and magnetism, we can maybe have orbital effects. And we know sometimes even the orbital effect is quite large. And this has brought Kane and Mehle to the idea that maybe in material, as a spin-orbit coupling, you can have quantum spin Hall effect based on the spin-orbit coupling. So they proposed it for graphene, which already shows a quantum Hall effect. But graphene is, if you see my periodic table here on top of the periodic table, and the relativistic effect for graphene is not so strong, and the spin-orbit coupling is not so strong. So graphene was maybe not the right materials to go with. Anyway, it opened the field of topology. So we in condensed matter physics and material science, we look for the topology of the electronic structure. The original concept comes from mathematics, where people simply look for the surface of an object. So if a ball or a cube are like this pancake. They have no holes, they have a simple surface. They have a different topology following this Gauss-Bonnet theorem to something like a donut and a coffee pot. Everybody likes to show this. And in Germany, we like pretzel. So we have 3 holes in the pretzel, and we like to drink alcohol in bigger quantities. So we have this, which you might get in a beer bar in Germany. So it's topological identical. So I have this very nice movie. You see, you can form a pancake into a cube, so they have the same topology. If something has a different topology, they are topological distinguished, and something special must happen. So you can transfer this idea to solids. And simply to tell you what we are doing is like, we like to grow single crystals, quite big ones, because if you really want to measure properties, it's better if they a few millimeters to centimeters, but we don't grow them arbitrarily. So we are not a typical material science group. So because we follow always the theory. So we like what Rosa is predicting. Most of the time it works. In topology, it works nearly every time. In correlated system is more difficult. Okay, it doesn't work all the time. Anyway, or we have some people in the group who do density functional theory, and then we make the material, we measure the material, and then we have a self-consistent loop in this sense, and we can look whether we really see the properties which were predicted by theory. So topology was for us who like to make magnetic materials and designed materials, and even looking for a high temperature superconductor where correlation plays a role and where we never were successful, a very nice field, because now we could do something and the prediction worked always. So we have many nice papers because theory predicts everything in the right way, because the concept is so easy. So simply applying this concept to simple semiconductors. So we all know a semiconductor has a valence band where the electrons, so this band is occupied, and a conduction band which is unoccupied, and we have the band gap. And depending from the strength between the atoms of a semiconductor, we have a large band gap, like in sodium chloride. So the salt in the morning is even without color. So because the gap is so giant, but we can have also the silicon, which has a smaller band gap. It looks shiny, nearly like metals. And we can have situation where we have an overlap between the conduction and the valence band. And this can lead, and this normal semiconductors we draw, so like the topology is like a pancake, but here in case of this overlapping situation, so this material were known for a long time, so people called it a negative band gap, and many of the heavy elements semiconductors, they have this band overlap. So especially because the s electrons, the inner s electrons, because of their high speed of the heavy elements, they move the outer s electrons lower in energy, and so this overlap is nearly in all the heavier element compounds. And it doesn't mean we need relativistic compounds. It's already started with tin and antimony, bismuth, and so on. So, and then because we have spin-orbit coupling, and spin is not a good quantum number, so this is always a forbidden crossing. So we open up a new band gap, and we again have a semiconductor, but this time we have a part of the conduction band in the valence band, and vice versa. And this is symbolized by the donut. So these two systems have different topology, and this leads to many new properties. So more or less, many of the compounds we know, we now can identify very new properties, even interesting for application, because they have, for example, very stable surface states, spin polarized surface states, similar like what you saw in the quantum Hall effect, which you cannot destroy, which connects the valence band and the conduction band. So my normal crystals are really insulating, like they look like the salt from the morning on your egg. Okay, so but the crystals which are have this topological inversion, they have this surface state where, similar like in the quantum Hall effect, the electrons and the spins are coupled, and they are undestroyable, because if I put water on the surface of my crystal, I simply move the topological surface state a little bit more to the bike, because it's a bike property. And the reason is because my surrounding vacuum is trivial, So it's a trivial insulator. So therefore, at the border between the topological and the trivial insulator, we have this singularity, which leads to this very special surface state. And indeed, people can see the surface state. It took some time to make these insulators really insulating, because the first candidate materials were quite difficult anyway. But nowadays, we are quite far in this sense. So for us, it was like working on this Häusler compound, what Rosa mentioned. I simply want to mention them one time today. It's like, these are simply relatives of the semiconductors, like silicon, okay? So you can, silicon has one element, gallium arsenide has two elements, and we simply take three elements, okay? So we like to make new materials, so we take three elements, and we can more or less design all the electronic structures which we know from silicon and gallium arsenide, but we can design many more electronic structures and many, many more compounds, and they're all existing, and we all made them, and many of them are trivial insulators, but many of them are also topological insulators. So this is even interesting for us, and we are growing really nice films with the group of Lorenz Mohlenkamp, because here we have superconducting semiconductors with the band inversion, and this might be interesting because they are not conventional superconductors to find the Majorana fermions in this material. Anyway, so these are details, but anyway, I want to tell you simply we can make materials, and more or less all the materials we know are trivial or topological. But the number of topological material we already recognized in 2010 when we found all these materials, that this is quite a large number, and the percentage of the semiconductors which are topological are quite high, so where we maybe find very interesting, unusual properties. So for us, it was also very exciting to have this spin momentum locking of the electrons, because this reminds us of the molecules. Okay, if we have a carbon atom, which has 4 different ligands, so then we have a chiral molecule. So we have this, what Christina explained in length, and I don't have to say so much. So we have the right and the left-hand molecules. So in the same sense, we have the spin. And the nice thing, as I mentioned already for the quantum Hall effect, is that we have now electrons which are not easily scattered, and we find even in some of our materials mean free paths of electrons which are millimeters long, so they are longer than the crystals. So, and we see kind of hydrodynamic flow of the electrons in this crystal. So this topology really has changed the world of condensed matter physics, I would say. And it's not surprising, because more of all the compounds, 25% of all the compounds we know are topological. So which means we simply know now where to look and to find these new properties. So it's really amazing for us, because it's the best time for us to make materials because it works so nicely. So despite of, you can say 25% of all the materials, so we have metals, we have semi-metals, we have insulators. And the reason is many of the metals are topological, because you can imagine this overlap between the conduction band and the valence band, or two bands in semiconductors, or two bands with different symmetries, parities, happens quite often in metallic system. But extremely interesting for me are also the semi-metals. So here, this overlapping area, which I already talked about, and which can be a forbidden crossing and lead to this topological insulator, can also be only partially forbidden. So here we can have the situation that depending from the symmetry of my crystal, if I have mirror symmetries, rotation symmetries, so this forbidden crossing doesn't open really up here, it's protected, and we can get this linear dispersion in the electronic structure, and we can have new systems which are the so-called Dirac semi-metals. This was already known from graphene. But if we even lower the symmetry, we can have even more interesting semi-metals, the so-called Y semi-metals. And the Dirac semi-metals, this is a potential solution of the Dirac equation. The Y semi-metal is another solution of the Dirac equation for massless particles. And the nice thing here is that we even have electrons which are chiral in the bulk of our electronic, of all our materials. So as I said, Dirac semi-metal, so we have these crossing points, very similar like here. and these points are 4 times degenerated. So it's simply if you move these 2 points back together, so they are in high symmetry, in the situation of high symmetry. So, but if we reduce the symmetry, we lower the symmetry by magnetic field or by putting strain on our material, we can turn them into wide semimeters. And then we have these 2 different crossing points, which are 2 times degenerated. And this leads to this chiral electrons in the bulk. And interesting new physics, because this Weil solution is already known in high energy physics, and people were looking for neutrinos, etc. So seeing this as quasi-particles in a solid is already interesting. So similar to the surface states we have in topological insulators, we also have here very special surface states, but I don't want to go into detail. I maybe even have not the time. But what is interesting is what people then recognized also, I think especially Wolowick at a very early time, that if we have this very special solid, so including helium-3, we had already was mentioned today, so we can maybe have situations similar like which are known in high energy physics, so which is related to the so-called chiral anomaly. And my background is chemistry and physics, but so I'm not the expert in high energy physics, and it's nice if you even find definitions of a very complex physics system in Wikipedia, but the chiral anomaly even made it into Wikipedia. So this is an anomalous non-conservation of a chiral current, and we like symmetry breaking. And it was originally formulated for the asymmetry between the elementary particles and the antiparticles. We heard about this already today. So we can have a situation that this symmetry between particles and antiparticles is broken based on the chiral anomaly. And the same you could imagine then in this Dirac and Weil semimeters, simply not with particles and antiparticles, with electrons and holes. So there was a prediction that you can see similar physics, and you could show the evidence for the existence or that these equations are correct. So this was very exciting for the condensed matter physicist working on topology, and many people tried to do experiments. We did also some experiment in this context, and there are many different experiments nowadays around there. And I simply want to show our examples. As I said, we don't deal with neutrinos or something. So Johanna has real particles, which we deal with quasi-particles in solids. We like to have this quasi-particle, so we are not looking for the hen, we're looking for the quasi-hen, okay, in ours. But anyways, the prediction was, so it's very, to break the, to observe the chiral anomaly, we need this additional term, this E dot B term, which means for the experiment is simply, we have to do an experiment, not like in a Hall experiment where we have the magnetic field perpendicular to the current. So here we have to have the magnetic field and the electric field in the same direction. And so we should see then that we break the symmetry at the beginning. We have the Weil points which have at the Fermi energy, and we have the same amount of electrons and holes. And then if we apply this E dot B term, we should get the asymmetry. A similar proposal was done in the context of the axial gravitation anomaly, which deals with entropy, to have additionally temperature gradient and measure the thermal conductivity there. So these are, as I said, a quasi-particle experiment, but we were super excited now since we had this material suddenly and this new viewpoint of the material. So we made this material. So I don't want to go here also in detail, so we can grow all these nice crystals. The good thing here is why this system worked so well is because it's quite easy to make. And you see here on the right hand, so it's the linear dispersion. This is photo emission, which is like a photograph of our electronic structure. And this was the scheme which I have shown you, where you have this 2 different chiral electrons. So you don't see the chirality in photo emission directly. If you have time, we might see it in other examples. Anyway, so this was already evidence that these materials are good materials. And I don't want to talk to this. And then we thought, okay, let's do the chiral anomaly experiment. So we do simply a measurement of the Hall effect, and then we switch the magnetization in the direction of current and look whether we see an effect, the so-called predicted negative magnetoresistance effect. And we see here on this side really that we saw exactly what theory has predicted. So then we did the same experiment applying also on our vial semi-metal, a temperature gradient. And again, here, this was the prediction from Zubair Sachdev and some astrophysicists like Karl Landsteiner. And exactly we saw also that if we sweep the field, we see that there's a big effect on the properties and exactly like the theory predicted. Okay, so even the power law was exactly like. So now this experiment was done also with chiral light, etc., to see in different ways chiral anomaly. Anyway, so you see really that it's very different whether you measure a Hall effect in the same crystal. You see this nice quantum oscillation. So we can really here in this wiggles, this resistivity, the magnetoresistance here versus the magnetic field. And you see the magnetoresistance is very distinguished if you have the B field in perpendicular to the current or in the same direction of the current. And yeah, so this was nice because it brought even this experiment into the New York Times. Everybody likes to see a simple tabletop experiment. So anyway, so but then there were new predictions. So since we worked in a very fantastic group with Andre Bernevik, and since we all have the spaghettis, and very often it's not so bad I like these DFT, but I also know material. So it was clear that we don't have only two-fold degeneration or four-fold degeneration in the electronic structure of our material. So we have also more than 2 and 4-fold degeneration. So what does it mean? And we can have chiral material, which have even a very strange electronic structure. So this has led to a publication where we did the theory and looked for materials. So can we have solution of the Dirac equation which go beyond Weil and Dirac fermions? Can we find other unconventional quasi-particles and maybe even more interesting properties? And this brought us even a nice commentary from Carlo Benacker, who cited Heisenberg, that Heisenberg also said, okay, so in high energy physics and astrophysics, we have this two solution, but if we would have a lattice on the universe, we might have more solution, which maybe could lead to new particles and beyond Weil and Dirac. Anyway, we didn't find protons who morphs in photons or some strange thing, and even Heisenberg had already the idea that this is strange. But anyway, it was even more interesting. So our focus was then on the chiral materials, because here we have quite a few chiral. So we can have molecules which are chiral, we can have biomolecules which are chiral, but we can also have solids which are chiral, and especially the solids which are chiral and have this very interesting topological electronic structure. So more or less, so what I said,
Claudia, we have like 5 minutes.
Yeah, in the Weil. What?
We have 5 minutes.
Okay, yeah. In the Weil system, so we have if we apply, if we change the magnetic field in the direction of the current, we can make an asymmetry between the left-handed and the right-handed moving particles, which leads to this chiral anomaly. In these chiral crystals, we can have the situation, we can make 2 enantiomers, and then each of the enantiomers is more or less showing a moment of this Weil semi-metals, where we can change the chirality by the magnetic field, which I think even is more interesting than the others. But anyway, so this was another system to investigate. And again, we looked for photo emission, so look whether we really have the electronic structure which we expected. We looked even with circular polarized light, and this is related to Christina's talk. We can see that the orbital angular momentum, which I think is maybe more important than the spin in all the system, so it's really nicely distinguished for the 2 enantiomers. And this makes it also interesting because we also like to bridge the world to the molecules, not only to high energy physics. So we see this fantastic chiral surface states. So because we can distinguish we cannot distinguish the electronic structure of 2 molecules, we cannot distinguish the electronic structure simple solids because they are exactly the same. Therefore, it's so difficult to separate these two enantiomers in reality. But here it seems to be topology and the topological phase make a difference. And this leads to even chiral surface states in these materials which are distinguished, which for us is interesting if we think about the broken symmetry maybe in Origin of Life, which was introduced by Christina. So we use this to show that we even can have absorption of chiral molecules depending on the chirality of our solid. So at the end, so what is a big thing, what we would like to do? So we like to do to make a bridge with the same materials, which might explain the asymmetry between matter and antimatter, is maybe useful to explain why there is an asymmetry between the molecules which we are made of, the DNA. So we see that we here can use this topological materials even to do enantioselective absorption. And this brought us to a collaboration with Ben List since 2018. Meanwhile, he's very busy since he got the Nobel Prize. So for chiral enantioselective synthesis, but we still think we can make many of these interesting experiments. And with this, I come to the end. I don't want to say the summary, but I was super happy to see Johanna's talk and Christina's talk. And I know that I have to learn a lot. And I think that this field of chirality is super exciting, and to bring topology and chirality together might be also an interesting way to understand different fields of physics. And yeah, this work was done with my nice group and fantastic collaborators. And I thank you for your attention.
Thank you very much, Claudia, for this inspiring talk. So now the talk is open for discussions and questions, and I see that there is already one question. Let me just read the question by Salman Zaman. The question is, do you think a band gap can be minimized by some doping techniques? And if yes, then what is the criteria for the selection of doping materials? For example, if I want to minimize a band gap of carbon, a carbon nanotube, then which compound is most suitable for doping? Thank you.
So carbon is really changing. I would say our systems, which have already two elements, is much easier to dope, honestly. This is exactly what we do. We have one really fantastic collaborators, Said Hassan in Princeton for photoemission, and he always wants us to design the topology of the material by doping. But carbon is quite challenging because I think carbon nanotube, to dope carbon nanotubes is really, really tricky. So I would say if I want to do something with carbon, I think the twisting is much more interesting and possible. And I think to design the electronic structure in twisted graphene, which can be made also chiral, by the way. And and then you are with gating is maybe the way you have to go if you want to do it with carbon nanotubes. This is or maybe drill the carbon nanotube. So theory should predict where we have to go.
Okay, thank you very much. There is another question by Aidan Garibli. And the question is, thank you for the interesting speech. Which methods do you use to obtain new materials? It's a very general question, Claudia.
Yeah, no, but it's a very good question. So, so we use different methods. So we simply use all the possibilities which we have in the labs. So because if there's an interesting prediction, we immediately want to do materials. So we have synthesis methods. So we simply take two elements, melt them together, and if they have a simple phase diagram, we are maybe lucky and they grow single crystals, or we need a liquid like salt in water. You know, you can grow as a kid already nice single crystals, which I did with my nephews and niece and my daughter, and hopefully soon with my grandson. I'm looking forward that he's able to grow crystals. But you can also do very complex systems like laser-based floating zone methods and so on. It simply depends on the phase diagram of the material.
Okay, thank you very much. For the moment, I don't see more questions in the chat, but I have a question. So in this last suggestion that or idea where you want to bring together the world of crystals with the world of molecules. Which is exactly the idea behind there? Do you want to do basically hybrid systems where you bring together molecules or chiral molecules and chiral materials? What exactly is I see the pictures, but what exactly do you want to, is your plan?
So there's a boring plan. I take a chiral crystals. So what Ben Lister did is like he put chirality in and get chirality out. Okay, therefore I was very much excited by the talk of Christina, because she said she can select the chirality, structural chirality by light. So what we also want to do, we want not to put chirality in to get chirality out. Okay, so it's much more interesting if we don't have structural chirality and get chirality out. Okay, so the light idea was already a nice idea. So my idea is if we could take a non-chiral crystal like the wild semi-metal, and this is a quite little bit tricky experiment, but I think we're on the way. So if you can put no chirality in and get chirality out, this is the next thing, okay? And this is what we are working with Ben List. So one issue is really intensity. So we work with crystals, you don't have a giant surface, so to see signals might be a challenge. But I think the big thing is, can we put non-chirality in and get chirality out? And this is why I think also is the most exciting question of Johanna, I assume, no? Okay, so this is a big thing. Okay, we want to do, so one concept which people have, that the spin might be important. There's this chirality-induced spin selectivity, so that you can get spin polarization based on chirality, not on magnetism, which means also you have maybe the reverse situation that you can get chirality based on the spin. So these are all questions also related to how could we have a fundamental broken symmetry concerning the molecules we are made of on Earth. But at the same time, the asymmetry between matter and antimatter, people do high energy, heavy ion collision, I think also to show the asymmetry between matter and antimatter. And so our crystals, which have the same physics, maybe this, I think, is super exciting.
So we have one more question from Garcia Page. Could these studies you show about OAM shed some light on chiral superconductors? So what can you say about chiral
superconductors? Very good question. So the question is this orbital angular momentum. Okay, right. So what we see is that the orbital angular, so one of this, what we calculate in case of topology is the Berry phase, and the Berry phase is related to the orbital angular momentum, which people who have light likes and people who have molecules like. So it's also some common thing which breaks symmetry. And this is a good question. Okay, I would say honestly, yeah. So because some people now thinking, so this is, for example, a new superconductor, which even where we can set the chirality. And if we have a chiral superconductor, we break fundamental symmetry and we maybe get unconventional superconductivity and could find Majorana fermions. And in this material, we really showed now by the magnetoelectric effect, so that you can set the chirality with a magnetic field. You can set chirality eventually also in some systems. This is quite new with chiral light. But so you have a non-chiral material, you make it chiral in a magnetic field, or you make it chiral with light, but you can even switch the chirality from one to the other. And this means chiral superconductivity is unconventional superconductivity. And this chiral materials, they have also large orbital angular momentum. So the question is, there a connection? Is a good question. Mm-hmm. But we don't know.
Okay, I think we reach now thank you very much, Claudia, for answering all these questions. And thank you very much for all the speakers for answering the questions. Thank you very much to also the audience that have been following the talks either in the Zoom or in the YouTube channel. And tomorrow we are continuing. So I pass now the word to Claudia. Claudia, you already talked. I'm passing now the word to Laura. Laura, do you have some last words you would like to say today?
Maybe just 2 sentences. So thanks everyone for joining. Thank you to all the plenary speakers. It was a pleasure for us to have you. So thanks for participating today, and we will continue tomorrow at 2 p.m. my time. So I will send a reminder shortly before we start, also again with the Zoom link. So yeah.